Okay. Hello. This is D-form. And so last time we were just talking about matrices. The last thing we talked about was transpose. Actually, before I go into that, let me get this on here. I just mentioned this. But so the quiz on Wednesday will cover the daily assignments from Monday the 11th, Wednesday the 13th, and today. Not Monday because there's no school on Monday. What? There's a vector assignment too. Yeah. So yeah, just look in the daily assignments. There's all the ones that are up there by the end of today are going to be the ones that this quiz is on. Before I start with new stuff, does anyone have any questions about last time? Okay. So there's still some matrix stuff we have to talk about. So first, let's talk about square matrices. So far, everything we've been talking about is generalizable to any shape of matrix. But a square matrix is one with the same number of rows and columns. An important thing in a lot of square matrices is the diagonal elements. So the diagonal elements of a square matrix are the elements where the column number equals the row number. So, for example, if you have this matrix 1, 3, 1, 2, 2, 4, it's funny that I'm giving an example of this matrix, and I'm like reading the numbers off here I wrote, when obviously I just made up 9 numbers, you know. Not like ha-ha funny, but more like odd funny.
You ever done stand-up?
No. Okay, so the diagonal elements are these 3 because it's row 1, column 1, row 2, column 2, row 3, column 3. Okay. One special case of square matrices are symmetric matrices. So a symmetric matrix is a matrix M where M is equal to M transpose. That can only happen with square matrices. If you know, try to fiddle with the numbers on a matrix that isn't square, and you'll see why. But like, for example, 1, 3. So the one I have here, the example I just did, before is not symmetric because the 2-3 element, the 1-2 element isn't the same as the 2-1 element. Okay, so when you transpose them, that's going to be different. But this one is symmetric. Because all the off-diagonal elements, if you flip the subscripts, you get the same value. Yep.
Is that why you talked about something like special, like important numbers and matrices and matrices last time, like the diagonal and the corner ones are the important ones, like there's a symmetry between them or something like that?
Yeah, well, the diagonal, these can always be anything. Symmetric matrices are going to be important in our for this whole class. So those can be anything, but in a symmetric matrix, you have to have this matching between these, the top triangular elements and the bottom triangular elements. So one thing to notice, for us, our stress tensors are symmetric matrices, and they're 3 by 3. And so that's what's really important to us is 3 by 3 symmetric matrices. And it's worth keeping in mind that any symmetric 3 by 3 matrix has 6 independent elements. The matrix has 9 elements, but 3 of them have to match the other 3, so it's 6 independent elements. Okay, this is the first thing, and that's really important. And this is the other thing, also really important. One nice property of symmetric matrices is that the eigenvalues are always real. You don't have any complex eigenvalues. And the eigenvalues of the stress tensor are going to end up being an important thing to us. So only real eigenvalues. Okay, well, we haven't talked about that yet. I bet some of you have heard of that in classes before or whatever. It'll come up in not too long, and I'll explain it carefully. But when we get to it, I'll emphasize, why it's important that the ones we're getting are real, because they don't have to be. They can be complex. For now, they're just a thing with a cool German type name. Okay, matrix multiplication. So we're going to have to do a lot of this. That's the next topic. So you can think of this as just a series of dot products. And so, well, you know what a frickin' dot product is. I don't know. I have it written here, so I'm going to write it. 2, 1, -2, dotted with -5, 0, 6. So to take that dot product, that would be 2 times -5 plus 1 times 0 plus -2 times 6. So you get this. It's a scalar value. It outputs a scalar value from 2 vector inputs. To multiply matrices, each output element so say our output matrix, our product matrix M, each of the elements are, an ijth element, and that Mij element is the dot product of the left matrix's ith row and the right matrix's jth column. So, for example, let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that symmetric or not? Nope. And we're multiplying it by 10, 11, 12, 13, 14, 15, 16, 17, 18. And so what you get if you do this is 138, 171, 204. I'll talk about these in a second. Let me just get the right values down here. 174, 216, 258, 210, 261, and 312. Okay, so the way you get these values, to get this 138, that's a dot product between the first row and the first column, because that's I is 1, j is 1. To get this 171, that's a dot product between, well, let's think about it for a second. So what are the row and column numbers of 171? 1, 2. So we're going to take the first row of this one and the second column of this one and dot product, and that gives you that answer. How about this one? What row is that? Second and the third column. Okay. Really, for these to be useful, you don't even have to know that, because your calculators will do these calculations for you. And if they didn't, this would be a pretty cumbersome approach. But since it's so easy to get calculators and programs to do matrix calculations, this ends up being a really nice way to do these calculations. So in your calculator, you just go, you could do this as like 1, 2, 3, semicolon, 4, 5, 6, semicolon, 7, 8, 9. So that's that first matrix. And then just use the regular multiplication function. 10, 11, 12, semicolon, 13, 14, 15, semicolon, 16, 17, 18. And it'll spit out that answer, if that answer is correct, which I hope it is. Okay, one important thing to notice about matrix multiplication. If you remember only one thing from this class, okay, it's probably something other than what I'm about to tell you right now, but this is also very important, okay? The order matters in matrix multiplication. In other words, AB is not equal to BA. And if you're not dealing with square matrices, then one of these could be possible and the other one would be impossible. You can multiply more than one matrix together by just doing them two at a time, and then multiplying the next one on the right or the. And this might be sort of surprising because the order of, which one's on the right and which one on the left matters, but the grouping does not matter. Well, obviously more than one. What I meant is more than two. There's not really any such thing as multiplying one matrix. Okay, you can multiply more than two matrices. And the grouping doesn't matter. So what I mean by that is A, B times C is equal to A times B, C. All that matters is which one is on the left and which one is on the right. Okay, you can't switch the order of them. So the last thing I guess I want to say about matrices is you can multiply. In this class, square matrices are going to be more important. You can multiply matrices that aren't square. As long as the number of columns in the left matrix equals the number of rows in the right matrix. Otherwise, you can't do that dot product. You know what I mean? So as long as the number of columns on the left matrix equals the number of rows on the right matrix. And in fact, you can think of the dot product as really a matrix multiplication. You can think of it as like 1, 2, 3. So that's a 1 by 3 matrix multiplied by a 3 by 1 matrix. That gives you the dot product. Okay. Any questions about any of those calculations? Okay, so very soon you should take the time to get comfortable doing that in your calculator. Make sure you know how to enter matrices. You don't want to spend any time doing these by hand because they just take forever. Because the matrices we're going to use are 3 by 3 and it's just a lot of multiplying. Okay, so now we're finally done with the math that we needed to cover. So now we can start talking about the main topics of this class, stress and strain. So I'm going to first start by defining stress. And the form of stress is a tensor, the same way as like velocity is naturally a vector, or acceleration is naturally a vector. Stress is naturally a tensor, and I'll talk about what that means. So if you're trying to predict damage in a loaded member, trying to predict damage to an object under loads, first, you calculate the external loads. And that's what most of statics was about. And then, in certain cases, in beams, we can go from there to get a little more information about how likely this thing is to fracture by calculating the internal loads. But the internal loads, if we're looking at a beam, they actually give us values along this whole line. They don't differentiate at all between like whether the geometry along this line is different than it is on some other line. And so it does, and it also doesn't make any distinction between the different points in the cross section. Okay, maybe it's more likely that a fracture would start at the center of the beam. Maybe it's more likely that it would start at the top or the bottom, and we can't make those distinctions with internal loads. So we'd like to have a more detailed definition, a more detailed quantity that would let us differentiate between the different loads, between the different points in the cross section. So internal loads give us information about an entire cross-section of a beam. What we really want is information about the points. And so the way we're going to do that is we're going to, so here's the object. And we're going to imagine a cubic chunk of material on the inside. Okay, so what is going to, what's happening in general on the faces of this cube? I mean, this is a, that cube isn't different from its surrounding. It's just we're deciding that the piece that we're going to isolate for our calculation is this cubic shape. Okay, so we have fixed joints between the faces of this cube and the surroundings. So what kind of loading do we have on the faces of this cube? Well, it's a fixed joint, so what kind of load do we have at a fixed joint? That's right. So, and this is 3D, so we have a full force vector on each of these. And then we also have a full vector couple. And that's happening on each one of these faces. Those double arrows are the couple components. What? Oh, yeah, so we did the circular one in 2D, but in 3D we'd have to do it about each one of these axes. So people use those double arrows instead to indicate that those are components of a moment. So each one of these double arrows, you can think of that as like a moment acting about that axis. Okay. So each face of the isolated cube is subjected to a full force vector and a full couple vector. We didn't see a lot of those in statics because we pretty much did everything in 2D. And these are due to the fact that the contact between each face and the surroundings is a fixed joint. And that's the idea of, that's really the key idea for the stress tensor, except this is a macroscopic thing, and we want it at every point. So we're just going to do a limiting idea to get this cube down to an infinitesimal cube. Okay. But that does one thing that is important. So what you get is the stress element at a chosen point. Something happens to those couples when you limit all the way down to zero size. Okay, so now this is infinitesimal. So think about what a couple is. Mathematically, we treat it like a pure moment, but that doesn't really tell us what the issue is. What causes a couple is equal and opposite forces acting at some distance from each other, right? You can't have a couple without equal and opposite forces acting at some distance. So if this cube has a size, it's an inch, cubic inch or something, these couples are caused by those equal and opposite forces acting like an inch apart, right? Or less, but some distance apart. As we limit down to 0 size, those equal and opposite forces shrink down to 0 distance. And so in the limit, we lose all those couples, okay? And we're left only with forces. Well, those forces actually go down to 0 too, but if you take a ratio of the forces to the surface area, those don't disappear. And so we're left with a thing like this. Where each face each face has a vector of force per area loads. The couples go away in the limit. All right, so how many unknowns do we have in the stress for one point now? So okay, the traction on each face, here's where we are now. What we'll call the traction on each face is the force vector per face area. So each face has 3 values, right? 3 components of force per area, 3 components of traction. We have 6 faces, so that's 18 total values of traction in the stress element. This gets reduced, though, because we're going to assume that these things are in static equilibrium. And because of that, there are requirements on the relationships between these. Like, for example, this component of traction that's pointing to the right has to be balanced by a component of traction on the opposite face pointing to the left. Okay? So requiring force equilibrium tells us that the information on all the negative faces is redundant. Like if we know what's going on this face, then we know what's going on the opposite face. It's just equal and opposite. Okay? All right, so requiring force equilibrium tells us that the information from negative faces is redundant. Okay, so just like that, half of our, we had 18 values that were representing this state of stress. We just cut half of those out, so now we need 9 numbers to represent a state of stress. 9 values needed to represent the stress at a point. And then requiring, so this comes from like Newton's second law. Now we can also enforce the rotational equation, and we can eliminate some more of these things. So requiring moment equilibrium says the traction component there has to equal the traction component there. So these have to be equal and opposite. Equal magnitude. These have to be equal magnitude. And these have to be equal magnitude. And so now we've decreased the number of values we need to represent this state of stress by 3 more values, and so we have our final total, which is 6. Okay, and based on what we were just saying about matrices, and I said that stress is going to be represented by a square matrix. What kind of square matrix needs 6 values to define it? A symmetric. Yep. So let's see. So the final number of values required to represent a state of stress is 6. And these are the 6 independent values in the 3 by 3 matrix that defines the stress tensor.
Stress tensor, is that, what is that referring to? Exactly the cube?
So you can think of the way, so like what is a vector? Like a vector is an arrow, right, that represents a magnitude and a length. And then mathematically, to do math with it, you represent it as 3 components, okay? A tensor, you can think of this cube, you can think of that as being what a tensor is. It's a physical mathematical object that's a cube with these arrows all over it. And if you want to do math with it, you represent it as a matrix. It can have different sizes. For us, it's 3 by 3, and this one happens to be symmetric. So, okay, let me give you the final definition of Okay, well, so what are the units of stress? We're talking about forces divided by areas. And so in SI units, that's Newton per meter squared. Which is pascals. And the stress values that we're going to get, when in engineering applications are so big that a lot of times people use megapascals or even gigapascals. But this is the SI units. Okay. And here's the final definition of the stress tensor. Okay, so there's the stress element. Those faces correspond to the directions of the coordinate axes. So the ones that I'm drawing here are think of each face as being defined by the axis that comes out of it. Okay, so this would be the positive x face, positive y face, positive z face. The other three that we don't see are the negative x, negative y, and negative z. But we don't need to draw those because of the redundancy. And there are 9 values. Only 6 are independent. And these are sigma xx. So the naming convention of these is the first subscript is the face that you're on, and the second subscript is the component of the vector. So this is the stress element on the x face in the x direction. This is the stress element on the x face in the y direction. This is the stress element on the x face in the z direction. Okay, and then on the positive z face, we have the same kind of things. The one coming out of the z face, what would be the name for that? Yep, ZZ. How about the one in the positive x direction? ZX, ZY, and then on the Y face, there's the YY, YX, and YZ. And this corresponds to the matrix, the stress tensor, in this way. So mathematically, this is represented as sigma xx, xy, xz. So now this one, this would be the yx element, but because of what I said before about equilibrium, we know that the xy element has to be equal to the yx element. That's what gives this matrix its symmetry. So I'm just going to write this again as xy. Okay, those are the same value. Then yy, then yz, and then xz, yz, zz. So you get this 3 by 3 matrix that's symmetric, so only 6 independent values, and it represents this physical stress element. symmetric. So, 6 independent values. The diagonal elements of the stress tensor are called the normal stresses. So look at that stress element and look at where the diagonal elements are on the stress element and see if you can make sense out of why these are called the normal stresses. So the diagonal elements are this one coming out of the x face, this one coming out of the y face, and this one coming out of the z face. Those are normal to the faces. So they're called the normal stresses because they act normal to the element faces. And they represent tension and compression in the material. Tension if they're out of the face. Which means the value is positive. And compression if the values are negative and then they're pointing into the face. Okay, any questions about that? All right, let's stop there. Next time, maybe just in one class, we'll talk about definitions of strain, and it won't take us too long to give these basic definitions and talk about the relationships between them, and then we're just going to spend the rest of the time talking about in what cases can we actually calculate what these stress values are, Okay.